The first talk of this morning is Simona Settepanella. Will be about combinatorial Morse theory and minimality of hyperplane arrangement. We're very happy to have you here.
Okay, so first of all, thanks to organizer for inviting me. Very nice place with many young people. So it's fun. And okay, this is a very old work of mine. It has 16 years old. So some of you were probably in elementary school when I did this. The reason why I choose this quite old paper is that it seemed to me it fitted more the topic of this conference. And also because, okay, I am from Abruzzo. Abruzzo is a region in which there are a lot of sheep's land. And so we say, so you don't throw away anything of a sheep because you use the wool for jacket, and then sorry, with vegan and vegetarians, we have a lot of delicious dishes. So same for papers. You never know. You don't have to throw away anything. You never know when it pop up the moment someone will be interested in your 20 years old paper that you thought was no one interested in. So besides this, when we wrote this paper, this construction was a mean to an end. So we were interested in doing some computation, and we built this construction. But nowadays, that the combinatorial algebraic topology is becoming more and more interesting, especially for young people. I think this is now an example. This was one of the first examples of a successful application of discrete Morse theory to reduce a given CW complex. So I thought that maybe some of you could have been interested in this example and check and get some idea of how to use maybe similar construction to reduce your CW complex, okay, or your simplicial complex, okay? So, and also for this reason, I will try to keep things as simple as possible, because I would like to give you an idea of the ingredients so that if you are interested, you can dip the knowledge and check if you can use something I'm giving to you, okay? So of course, I will start with the motivations we had at that time for this construction and some basic fact on discrete Morse theory that you probably know, okay? But this will be embedded in our construction. And then I will tell you about the minimal CW complex. Okay, I have this, which, yes, where, two. Here, okay. And something about the minimal CW complex. This minimal CW complex has been built starting from a given CW complex that was the Salvetti complex. Maybe some of you already know it, but I will provide an example. This complex has been extended in many different ways, okay? And from this complex, applying discrete Morse function, we described the minimal CW complex underlying this one. And then I will provide an example, which is probably the most interesting part. Okay. So where we start from, at that time I was studying, which I'm still studying, arrangement of hyperplane. Nowadays, I'm studying this object, which is called discriminantal arrangement, that I love, but as I said yesterday to my companion, I am the only person interested around doing this discriminantal arrangement. But by the way, so if you have an arrangement of hyperplane, so just a bunch of hyperplane in the real space, and you consider the complexified arrangement, essentially you just are considering hyperplanes with real coefficients, with defining polynomials having real coefficient, and you look at them inside the complex space. So this is the complexification. And you are in this case, then what happens is that the complement has variety and has its own structure, okay? Like points, for example, the easiest is the point in the complex line, okay? So this complement has the same homotopy type of a CW complex that was defined by Salvetti in 1987, okay? So the Salvetti complex is a CW complex having the same homotopy type of this complement. And the idea was, okay, let's use discrete Morse theory and see if we can obtain the minimal version of this complex. Minimal means that the CW complex we obtain has a minimal number of cells. That is as many cells as the Betti numbers, okay? I mean, this is the most we can, of course, do when we consider a CW complex, okay? Why we were interested in this? The main reason was to find a simple object to compute the cohomology of the complement with the local coefficient. The cohomology of the complement with integer coefficient is known, is the very famous Orlik-Solomon algebra, very famous for people working on arrangement of hyperplane. But probably you have seen, if you work a bit in combinatorics or in topology, in algebraic topology, at one point you met an object which is essentially the Orlik-Solomon algebra, even if you don't recognize it, okay? And this problem was and still is object of study by essentially all the people working on arrangement of hyperplane, and not only. Of course, we still don't know almost anything about that, not even at the H1 for lines, and so something more is known for the case of line, so the H1, okay. Sorry. Okay, why we were sure about the existence of a minimal complex? Because there was already a result by Dimka and Papadima in 2003 and Randall in 2002. They separately essentially proved that the complement of hyperplane arrangements in the complex space is always a minimal space. So this was a guarantee that minimal CW complex indeed existed. Yoshinaga slightly refined his result in case of complexified real arrangement. He found something that was minimal, but his description was not very easy to handle, and the boundary map was essentially almost not provided, let's say, okay. So we started, the idea was to use discrete Morse theory, apply it, as I told you, to the Salvetti complex. So first, let's see basic tool of discrete Morse theory that you probably know. So if we have a finite regular CW complex, and K denotes just the set of all cells of M, K will be partially ordered by inclusion, and KP is just denote the cells of dimension P, okay? So we have a discrete Morse function is just a function that goes from K to R, which satisfy for any cell of dimension P the two conditions that the cells of dimension P plus 1 bigger than this cell, sigma P, on which the value of the function is smaller or equal. This set contains at most one element. And in a similar way, we ask that the cells that are smaller, in which the value of the function is bigger or equal, this set has cardinality smaller or equal than 1. This essentially mimic, it's a total mimic of the Morse, the definition of Morse functional varieties. And in particular, we will say that a cell is critical of index P if the cardinality of these two sets is 0. So for the people who doesn't know this, the meaning is what happened is simply that if you have a CW complex and you can find a discrete Morse function on it, then you can collapse your complex to another complex, homotopically equivalent, so bringing the same information, in which the only surviving cells are indeed the critical ones. Okay. So it's just a way to collapse your original complex to something that is exactly the same. It's homotopically equivalent in mathematics is exactly the same. Okay. So, of course, as happened in the continuous case, to find a Morse function is a nightmare. So let it go, the idea of finding a Morse function. What is easier to be found, and what we did indeed, is to describe the discrete gradient vector field. Okay. What is the discrete gradient vector field associated to a function f? Of course, if MPF denote the number of critical cells of f of index P, then we can collapse, as I told you, to a CW complex, a new complex with the same number of cells. So let's define the discrete gradient vector field VF of f. This is given by all the couples, sigma p, tau p plus 1, on which the value of f on tau p plus 1 is smaller or equal than the value of f in sigma p. Okay. So to go from f to VF, it's very easy. Okay.
The sigma and tau are not one less than...
Yes, we asked that. I just gave it for granted, sorry. Yeah, sigma p, of course, is smaller than tau p plus 1. In our context, essentially, it means that it's in the boundary, okay? By definition of Morse function, what happens is that each cell belongs to at most one pair of VF. This condition is essentially the only conditions to define a vector field associated to a discrete Morse function, because we have that a discrete vector field V on M is a collection of pairs, sigma p tau p plus 1, with sigma p in the boundary of the tau p plus 1, of cells, such that each cell of M belongs to at most one pair of V. So every time we have a set V, we can define a set V having this property, then this will be the gradient vector field of a discrete Morse function, which is the information that really provide the discrete gradient vector field. We will see this with an example, but essentially this tells you how to collapse your CW complex. So essentially this means that you can collapse this cell on this. What do I mean when I say collapsing? It's just this process, right? So you have 2 0 cells. You have your 1 cell here. Okay, this is homotopically equivalent to this point because you collapse. This is V0, this is V1, this is E1. So you collapse E1, you collapse V1 on V0 with E1, okay? So the critical cells is what is left. The gradient vector field tells you how to collapse, okay? So if we have discrete vector field V on our CW complex, a V path is just a sequence of cells, of course, of this type, in which, of course, sigma I is in the boundary of tau I, okay? Such that for each I, here there is, sorry, a typo, sigma I p tau I p plus 1 belongs to V, of course. So this is a path inside V. And sigma I p is different from sigma I plus 1p, okay? So as happened also in yesterday's talk, such a path is a non-trivial closed path if 0 is smaller or equal than r, and sigma 0 is equal to sigma 0, sigma r plus 1, okay? So, but in the difference with yesterday's talk is that we are not interested in the closed one, but in the open one. So a discrete vector field V is the gradient vector field of a discrete Morse function if and only if there are no non-trivial closed V paths, okay? So in order to describe a vector field, a gradient vector field, discrete vector field, we only need each couple to belong at each cell to belong at most to one couple. To be the gradient vector field of a discrete Morse function, then we don't have any closed, we do not have to have any closed V path inside. Okay. So let's go to the second ingredient of this talk, which is the Salvetti complex. So the Salvetti complex is the deformation retract of the complement of complexified hyperplane arrangement, okay? And so if we consider the arrangement inside the real space, this arrangement provides to us a stratification in what we call facet. And the K stands for the codimension. And then we can order S just by reverse inclusion. So Fi is smaller than Fj, even only if the closure of Fi contains Fj. Okay, now I want to give you an example because I think an example makes things understandable. And let's consider probably the easiest example possible, okay? Let's consider 3 lines intersecting in a point inside R2. For people familiar with arrangement of hyperplane, this is a section of the braid arrangement A2, okay? But that's not necessary to know. So which is the stratification we are looking there? Essentially, we have, for codimension 0, we have 6 elements that are called chambers. Okay. So the open here. And then we have 6 strata of codimension 1, which are this, which we can call F10, and then F11, F12, F13, F14, F15. Okay, so those are the called facet. And then we have just one facet of codimension 2, this intersection point. Okay, let's provide the stratification. The reverse inclusion tells us that you see the closure. If we consider, for example, the closure of C0, the closure of C0 contains what? So C0 is smaller than F01. This contains F10, F15, and of course, F2. So this tells us that C0 is smaller than F01, is smaller than F15, but it's also smaller than F2. They are all in the closure of C0. Okay. Consider that this construction is dual, so you can really play with this kind of construction because there are a lot of dualities going on here, which is one of the reasons this has been generalized in many cases. Now let's see what is a cell of this complex. The cells are related to the stratification, which is the reason why to build the Salvetti complex, we need a real underlying structure. There is an homotopically complex, which is homotopically equivalent to the complement of any arrangement in complex case, but it's really a nightmare. That's why no one knows about it, and the people who knows about it just know it exists. Okay, but it exists. So now you know that there is something. Okay, so the cells are just as simply the couple in which you pick one chamber, and here you pick a KD codimensional K facet, and this provide you a cell. So what does this mean in our context? That, for example, we have C0, C0. This is a 0 cell. Since C0 is essentially a codimension 0 phase, okay? What this corresponds, it's a 0 cell, so it has to be a vertex. This corresponds to a point that we choose inside this chamber, okay? And then attached to this 0 cell, we have 2 1 cells, okay? What are these 2 1 cells? This is C0, F10, and C0, F15. Okay. So those cells attach what to what? We have how many 0 cells here? Of course, 6. one for each chamber. So we have one here, one here, one here, one here, and one here. Okay. So is it fine for everybody? Just you have questions or okay. So this one cell connect what with what? Recall that this is the underlying real structure, but we are merging this inside C2. This tells us what? That we can go around our hyperplane, okay? So we can go from here to here. And this is exactly the edge which corresponds to C0, F10. The edge here going out from C0, crossing F15, corresponds to C0, F15. Okay. So what happened here, you have one, how many one cells? Just, okay, here should go down, but it's okay. And then you have this one, rolling around, and then here, and here, and here, okay? So you have 12. So here, okay, I will delete this. You have CI, 6 0 cells. And then you have CI F1I and CI F1I minus 1, because you go up and down, except for, of course, for C0, in which this becomes 5, okay? So you have for I, between 1 and 5, and then we have C0, F01, and C0, F15. I could have used modulo 6, but so you have 12 one cells. You see, this gives you exactly the homotopy type, right? You go around, and that's all. And then the last one are F2 is contained in the closure of all the chambers. So CI F2 are the 6 2 cells. Okay. And these complete your complex. Of course, except the way I built this, it's easier to see, except these 2 cells here that you can see how it is attached, because you can go up here. In general, we are in dimension 4, so we cannot really see how 2 cells are attached to our complex, but what we can see is the boundary, okay? So if you are working with the simplicial complex, of course, it's easy, right? We know that this is the 2 cells. It's attached like that. That's all. But here, it turned around using all the 4 dimensions of C2, okay? But we can understand how it is attached using the definition of boundary, okay? So a cell CFK is in the boundary of another cell DGJ, if and only if, of course, Fk is smaller than Gj, and the chamber C and D are contained in the same chamber of the arrangement AFK, which is given by all the hyperplanes containing Fk, okay? Let's see this in our example. Okay, clearly for one cell, it's easy. We can easily see that because we can see that in the boundary of this one cell, we have what? This 0 cell and this 0 cell. Okay. Is it clear for everybody? And how we see this? So can I cancel here? Just sorry, it's quite small. But... Okay, what is in the boundary? So we are interested in the one cell C0, this one. So we start from C0 and we cross F10. Okay. What we have in the boundary of this, we can see that in the boundary of this cell are contained the 2 vertices, this vertex and this vertex. So C0, C0, C1, C1, okay? And indeed, we choose the property F10 is clearly contained, is smaller than C0, and F10 is smaller than C1, because this space, F10, is contained both in the closure of the chamber C0, is the wall between these 2 chambers, so it's contained in the closure of this, and is contained in the closure of this one. So this first property is satisfied, and then we have to consider the arrangement A of F10. A of F10 is nothing else than this hyperplane that we can call H12. So is H12. H12 is the support of F10 and of F13. Okay. Support means the minimal vector space containing those facets. Okay. And if we look to this, what we have in the boundary, the chamber C and D contain in the same chamber of, oh, sorry, I made a mistake. Of course, in our case, F10, in our case, the cell we are looking at in the boundary of this, so we have C0, this one, and C1, this one. Their support is all the space. Okay. So the support of a chamber is all the space. So that's all R2. So essentially, the second condition is always satisfied. So the only condition that matters is the first one. Okay. So C1 and C0 and C1. Okay. Sorry, maybe I did some confusion on that. In this case, we are considering always real. So we consider the original arrangement. The reason is that the second condition required the chambers be contained in the same chamber of the other arrangement. So if you consider the complexification, this is always true. Okay. So I want to give you maybe I will give you the example of what is in the boundary of two cells, okay? So let's consider C0, F2. Now this is a two cell. What is inside the boundary of this? Okay. The first condition tells us that all the facet smaller, they provide one cell. Can I delete this? No. Okay, F2 is contained in the closure of all those walls. So each one of these will provide to us a face for one cell in the boundary, okay? So we have F10, F11, and F21, F31, F4. Oh my God. Okay. So we have 6 one cells. Okay. How we choose the chambers? We choose them using the second condition. So we need to look now at those faces. So what is the support of this? There are colored chalks. Yeah. F01. The support is this hyperplane. So which are the chambers in the same chamber of this new arrangement? So means the same side with respect to this line, 1, 2, and 3. This one is the only one having this as a facet. So we have C0. But this also tells us what we have for F13, which is the chamber on the same side of C0, having now F13 as a wall, C4. So we know that here with F13 we will have C4. Okay. So our boundary, in our boundary we have C0, this one, and also we have this one. Okay. Let's redo the same construction for F11. So now the chamber on the same side of C0 are C0, C1, C5. C4 here, you mean? Because F13, the support is the same line. So you need to look which are the chambers that stay in the same side of C0. It's our C4 and C5. C4 is the only one having F13 as a facet. Yeah, should be below. Yes. You can also like manage the order somehow. You can show that those two indeed are equivalent. Because you contract in the same way. In the end, they are essentially the same. And the discrete Morse argument show this, because indeed these two cells you collapsed all it. So it's kind of, but yes, it should be below. So you have this here because C1 is on the same side of C0. And here C5 is on the same side. So you have this one. And finally, you have the last one, which are this and this. Okay. Okay. The choice of being up and above, it's just it's for convenience, because you build using you have to provide an order. So the most easy order is the clockwise or anti-clockwise. And if you choose the clockwise, then this one goes down, or vice versa. But it's really just a choice to describe. Okay, so this is the complex, which was the most difficult part somehow. Okay, no, it was not. But if you understand the complex, then you can also understand how to collapse it. Okay. So the idea is to use discrete Morse theory to collapse the cells of this complex to their minimal ones. Okay. So what is true that finally, in order to describe a Morse function, as happened in the continuous case, what you really need is just an order. So the most difficult part is to find a good order on the facet of our complex. Okay. Indeed, there is this theorem, and I will maybe rewrite. This theorem tells us that whenever we have a pair with fj in smaller than fj plus 1, so this is in the boundary of this one, this belongs to the gradient vector field of a combinatorial Morse function, even if fj plus 1 is smaller than fj in this order we defined, and for any fj minus 1 contained in between these two, fj minus 1 is smaller than fj. The set of the codimensional phases, which are critical, is given by the couple CFK, by the cell CFK, in which fk is smaller than fk plus 1 for any fk plus 1, which is contained in the closure of fk, and fj is smaller than fk for any fj which is bigger than c and smaller than fk in the order of facet. Okay. I will show you how this works in an example. So the most difficult part is to find a Morse order. And this is a second idea that allowed us, the intuition that allowed us to reduce our complex. We use essentially the Lefschetz argument, because we know that if we want to study the k-dimensional part, we can just study k-dimensional spaces, what happened in k-dimensional generic section of our object, okay? So this is what we did. We applied a Lefschetz argument, defining what we call, what is just a generic system of subspaces. So, okay, now we cancel and remove this. So, I will tell you how it works in our example, because I think it's much more convenient. So we have our arrangement of hyperplane, okay? This is air with H12, H13, H23. So, and we complexify ahead. We go to AC, contained now in C2, while this is contained in R2. So we want to stratify inside here, okay? What means generic stratification? It means that any k-space intersect any k-dimensional vector space at essentially one, okay? So in this case, this means that we choose a point V0 inside one chamber, and then we want a space of dimension 1 which intersects generically our hyperplanes that are 3. So we pick a line in this way, V1. So we have V0, V1. V0 is contained in V1, which is of course contained in V2, which is all R2. And this provides us a generic filtration of a generic stratification of the space, meaning a stratification of R2, which is generic with respect to our arrangement, okay? How this tell us which are the critical cells? I will not give you, I already gave to you the definition via the theorem. I want to give you the intuition, the idea, and what we really used to describe those cells, which is another theorem that come like 5 theorem after the one I wrote for you, okay? What is the intuition? The truth is that I already knew which were those hell of cells, okay? So I just needed to understand why they were the ones surviving. Because when you study an object for many years, then you know it, but you don't know why, okay? Which, you know that something worked, but you don't know why, which was yesterday, our Celeste was telling us, yeah, this worked, but we don't know why. So, but why matters, okay? So I knew that somehow the cell, the two-dimensional cell attached to this should have survived. I knew that there was one chamber, 1 0 cell, because the minimal complex, in this case, what we know that B0 is 1. So we need to have 1 0 cell surviving. We know that B1 is 3 because we have 1 for each hyperplane. So something around each hyperplane should have survived. And B2 is 2. This was the most tricky part, the one that really told us how everything was working. Because how we choose, so here this means that something has to survive. It can be any zero cell, so it's easy, C0, C0. And then we knew that one for around each hyperplane should have survived. So let's pick C0. Remember, we call this C0, C1, C2, C3, C4, C5. This was F10. This was F11. This was F12. So I still have 10 minutes, right? Because I started 5 minutes late. This Japanese thing that you need to finish perfectly on time. Not 1 minute earlier, not 1 minute later. Okay, so the natural choice is simply to say, okay, I choose one cell for each hyperplane. Okay. And indeed, this was the, oh wow, this was the case. 1, 2, and 3. So C0, F10, C0, F11, C0, F12. And I'm telling this to you because I think this is the argument that maybe there is some possibility to be generalized for you. If you understand very well the argument, maybe you will be able to use this in your context, okay? Working with simplicial complexes. Okay, so which are the two cells surviving? What is very strange to say is that I knew that the two cells surviving should have been the one connected to these two chambers, nor other. Okay. So that was what helped us to finally understand how to use the stratification. Okay. So what happened is essentially that, so here we have C1, F2, and C2, F2. So essentially, in order to describe the critical cells, we needed to use the stratification. But how? So V0 is inside C00. So this tells us this V0. Okay. Then what happened? If we move, oh, here, sorry, this is C1, this is C2. What is the property of C0? If we move V0 inside V1, we arrive where? In this chamber. Let's call this V0 after we crossed F10. And then here we have V0 after we crossed F11. And then here, another point, okay, that we call V0 after we crossed F12. So we move Vi inside Vi plus 1, each time crossing the faces of maximal codimension, okay? And then what happened? What is C0? So those three are all bounded because they are point. So point inside a line, they are all bounded, trivially bounded. So C0 is just the opposite of this point. C1 is the opposite of this. And C2 is the opposite of this point. And this is the way we found the three cells that survive. This argument can be seen better in this case. So let's pick, if we move V1 inside V2, just passing F2, what we get? We get this new around V0. So we point around V0, we move our space, we get V1 just crossed F2. I just crossed, it's really just crossed locally, and it's with the Lucchi, we proved it's combinatorial argument. Okay, so now we chart the chambers. If you look now to V1, F2, this line inside V2, we chart the two chambers that are bounded in those lines. So along those lines, we have four sections, one here, another here, and this one. So this is unlimited. So how it looks like if we pick V1, F2, here we have the intersection with H2, 3. Here we have the intersection with H1, 2. So this is C0. This is C5. This is, oh, I forgot H1, H2, 3, H1, 3, H1, 2. This is C5. This is C4. This is C3. C0 is unlimited, is unbounded. C3 is unbounded. So our bounded chambers are these two. We chart the opposite of these two with respect F2. C5 with respect F2, the opposite is C2. C4 opposite to this is C1. So these are the critical one. C4 is this one. So at this point, how we collapse it? The collapsing, it's easy to see in this case because what happened? So the green are collapsed. So this point is collapsed along this. This point is collapsed along this. Just collapse. This here is collapsed along this. So you essentially get your point inside your V0 here, and 1, 2, and 3 here. Same happened here. C5 is collapsed here. C4 is collapsed here. And then you are left. C3 also is collapsed here. And the other two cells, they collapse the remaining one cells. So the two cells, C3F2 is collapsed with this. the two cell here is collapsed with this, and the last one is collapsed with this. And so you have 4 two cells that collapse. Okay, and another one here is collapsed with here. Here. This is same point. This is same point. So the pink one tells you how you collapse the two cells. The green one tells you how you collapse the one cell. Okay, and then you have your minimal complex. The order that is the key is given just moving around along those spaces. So V0, so consider here has happened when you do proof, there is the underlining idea, and then there is the proof, the construction. So the Morse order that could be of interest for you, how we get it? Okay, we fixed V0. So V0 tell us that C0 is the smaller one. What is immediately after C0? We move V0 inside V1. So we intersect what? F10. Moving again, we arrive where? We arrive in C1. Moment. In C1. I'm too violent. C1, okay? And then moving again, we intersect F11. And then C2. And then F12. And then C3. Now what? Now is the turn to move V1 inside V2. So when we move V1 inside V2, so this order, we move V0 inside V1. Now we move V1 inside V2, which is the first cell we met, of course, F2. As soon as we move this, we meet F2. And then here, we move what? We again move V0 inside what I called V1, F2. And in this way, what we pick? From C0, we pick F15, and then C5, F14, and then C4, and then the smaller one, which is F13. And this provides the order. And if you check the order and the information I gave to you, unless I did some mistake because it's 16 years, I don't work with this stuff anymore, you should exactly get from the theorem I provide you, using this order, you should get these critical cells and the vector field to collapse. Okay. So that's all. I finished. Oh, thank you.
Are there any questions?
Is the right intuition to which cells are going to survive maybe the fundamental group in case of a two, if this complex is two-dimensional, then we know what the generators are supposed to be, like how many loops and then how many relations by the two cells?
Yes, for the one cell, yes, because this you are talking about the fundamental group. So for the fundamental group, you are just interested in 0 cells and 1 cell.
And the 2 cells for the relations.
the collapse.
Yeah.
Yes.
Mm.
The problem arises when you are considering higher dimension. Okay. So.
But at least maybe for the two skeleton, can we do you know if that's a good kind of estimate on?
Yeah, you know that you have to survive, and then you know that if you know that the fundamental group, especially in case of arrangement of hyperplane, it's easy because you know that you have as many cells as the hyperplane, one here, and then just Euler tells you the dimension here. Yeah.
Okay.
So this is, of course. The problem is that sometimes you need to know which one are the interesting one depending on your problem.
Yeah, I have a question about if you take deposit of strata in your stratification of the hyperplane.
Mm-hmm.
I mean, like the point inside the 6 one dimensional strata, and then that's and then the chambers.
Mm-hmm.
So what is the relation between the nerve of this poset and the Salvetti complex, if there is one? I don't know.
Yeah, I think I guess, well, I think they are essentially same thing. Which was one of the way that was used to generalize the Salvetti complex, I think, but I'm not totally sure about.
Okay, thank you.
Okay, but more discrete Morse function so far ask for regularity to work, if I remember well. You mean the complex we start? Yeah, the Salvetti complex is CW regular complex, yeah, so. So yeah, my answer was correct. Paolo is comforting me. Yeah.
Okay, Salvetti complex is about complexification, but there is also generalization when you tensor with Rn, like the Concini, Salvetti generalization. Does this your work also extend to that case?
Yes, yeah, I think so. Let's say this is for maybe more generalization of their work somehow, because their case is, if I understood well your question, is essentially the quotiented case, right? It's you quotient by the action of the symmetric group.
No, I mean, you can, instead of taking complexification of a real arrangement, you can tensor with R to the n instead of R to the second power. So like you.
Okay. I think so, yeah, I think there is this was a problem, if I remember well, but I could be wrong again, because many years was addressed by Salvetti and one of his former students in and the work is published on Math Research Notice or something. I will tell you later, but yes, I think if I'm not wrong, that's this work already exists.
Okay, thank you.
Are there any more questions? If not, let's thank Simona again.
So I was talking about admissible trees that we need to introduce in order to have the description of admissible parts. So an admissible tree is a tree graph on M leaves. So having a tree graph means we don't have any cycles in it. So we want these trees to be rooted, meaning that we have a distinguished vertex. And then we are fixing the number of leaves, and we are labeling each leaf with a distinct non-zero natural number. And then we are also labeling the non-leaf vertices, meaning we are labeling the internal vertices And the label depends on the number of outgoing edges we have from each of these internal vertices. So let me give you an example. For example, let's take m equal to 6. And so we start with 6 leaves. And we want to label this with a bunch of numbers, distinct natural numbers. So now we draw some internal vertices. And yes, we want at least 3 outgoing edges from each of these internal vertices. And now we want to label each of these internal vertices with a symbol q to the I, where this I here is between 1 and k minus 2, where k is the number of outgoing edges from each internal vertex. So in this case, we have an internal vertex with 4 outgoing edges. So we want to label this internal vertex with q to the I, where I is between 1 and 2. So either we choose to label this with q to the 1, either with q to the 2nd. They are both fine, so we have to make a choice and we can decide this label. Now, for this internal vertex, we have no choices because the label has to be between 1 and 3 minus 2, which is 1. So this is a 3. And now this 3 comes with a degree, and the degree of an admissible tree is the sum of the exponents we find in its internal vertices. So in this case, the degree of t is 1 plus 2 equal to 3. Okay, so we have these objects, which we called admissible trees. And now, surprise, maybe not a big surprise, we can define admissible forests as graphs whose connected components are admissible trees. This makes sense. So what we really want here is that now the set of the leaves of this admissible forest is an interval of natural numbers starting from 1. So here we are just 1, 10, 2, 9, 3, 5. Now we want the leaves to be all the numbers between 1 and n. We labeled with all the numbers between 1 and n. And yeah, this is also not a big surprise. The degree will be just the sum of the degree of each connected components. So let's try to make this an admissible forest. I have to erase this, sorry. And so here we can add, for example, one connected component like this. I think 6 is still missing. And one can also add 12. Now we have to choose a degree for this 3, and it's either 1 or 2. We can put here q to the 1. So at this point, we have that this is a forest. We call it f, and the degree of this forest is the degree of the first tree. We already know is 3. The degree of the second tree, which is 1, and the degree of these 2 tree with 1 leaf, which is still a valid tree with degree 0. And so it's 4. Okay. So what we have here is this family of admissible forests, which are graded graphs. Yes. Now, let me go back to this slide. Okay, so now we know what admissible forests are. What we want to study is this other object, which are pairs, I'm going to tell you. And so these objects here are pairs of admissible forests and a permutation. So these objects are something like forest and a permutation. And this permutation is an element of Sk, meaning just a group of elements that permute k elements. And this k is the number of connected components of the forest f. So here we have a forest f, and if we call this f, an element of a, p, 11 would be a pair. This first element is this forest, and then an element of S3, because here we have 3 connected components that could be, I don't know, 1, 3, 2. Okay, now this is a valid example of an admissible pair. Now, of course, we had a degree on the set of admissible forests, and we would like to define a degree also in these pairs. So we already know how to define a degree on the set of forests. That would be just, again, the sum of the degree of each connected component of the forest. So we want to define a statistic or something, a function on this element of this permutation in order to define the degree of these admissible pairs, we call it P, as the degree of F plus something computed over that depends on sigma. Now, this something we are putting is LEC, which is a statistic that can be defined over Sn. And so now I would like to spend some time talking about this particular statistic that can be defined in Sn in order to obtain a proper grading on this set of admissible pairs. So now we're going to talk about this LEC statistic. Actually, the first thing I'm going to introduce in order to talk about the LEC statistic is the definition of hook. Hook is a definition that can be given in any for a list of natural numbers. Again, we don't really need them to be numbers from in an interval of the natural numbers. I just need a list of distinct natural numbers. And all I want to check is that the first element in this list is bigger than the second one. And then from the second to the last element, we have these numbers to be in increasing order. Yeah, there are a lot of very easy examples one can take. For example, I don't know. So we want to have, I don't know, 3, 1, and then 4, 7, 19. This is a hook. I don't know. Oh yeah, just notice that we have to have at least 2 elements in this list in order to define a hook. So also 3, 1 is still a valid hook. Now, the reason why we're interested in hook is that Gassel in 91 noticed that every permutation in Sn has a unique hook factorization. Yes, which means that every permutation in sigma can be written the following way: a certain prefix, P, and then a list of hooks. Now, let me give you an example of this hook factorization, and let's see why this is unique. And in order to do so, I will need a long permutation. Let's take sigma in S13. Told you it was long. Okay. Now, in order to get this hook factorization, we scan this representation of sigma starting from the right, looking for a descent. Okay. So 1, 2 is not a descent. 9, 1, here we have found a descent. Now, I put a bar here, and what we have is that this is a hook. Of course, we looked for a descent. We have one descent. Everything is done in increasing order because we looked for the first. We fixed the first descent. So here we found a hook. Now we start from here, from the bar, and we scan again, looking for another descent. Now you can see the first descent we find here is 5, 4. Everything after 5, 4 is in increasing order. So here we put another bar, and here we have another hook. Of course, we either go on and reach the final part of this permutation. Either what we get is that at the beginning of the permutation, we have some increasing numbers that obviously cannot appear in any hook. So in this case, we scan again up to 83, which is another descent. And then we have a bunch of numbers. This is the prefix, a bunch of increasing number that won't appear in any hook. And I guess that this way of finding the hook decomposition should convince you that this is unique, because I was forced to just find the hook from scanning from the final part. So in this case, we have 3 hooks for sigma, and then this prefix, which is 10, 13. And yeah, this is the unique hook factorization for this sigma. Now, we know that this hook factorization is unique, so it makes sense to use this to define this statistic LEC. And the definition is the following. So we take sigma, we look at its hook factorization, and then for every hook, for each hook we found in this hook factorization, we count the inversion we find in that hook. So let me go back to this example, and let's find the LEC statistic for sigma. Now we already have the hook factorization, so what I have to do is count the number of inversion I find in each hook. So for example, in H3, we have that 9, 1 is an inversion, meaning that 9 is bigger than 1 and is appearing before 1, before the 1, so now they are somehow inverted. And 9 is also bigger than 2. So we have that here we have 2 inversions coming from this hook. Let's do the same with H2. So we have that 5, 5, 4 is an inversion. And then we have another inversion in this hook, because 7, 11, and 12 are in increasing order and are bigger than both 5 and 4. So here we have only 1 inversion. And then looking at the last hook, we have 2 inversions. Of course, no inversion appear in this prefix, but we are not interested because we only have to count the inversion appearing in each hook. So in this case, we have that the LEC statistic computed here is 5. Okay, so let me say a few words about this statistic. So this is like in the study of Coxeter group, in particular in the study of this group Sn, there is a certain interest towards statistics. This statistic is what is called an Eulerian statistic. The most important Eulerian statistic known in Coxeter for Sn is the DES statistic, the one that counts the number of descents in sigma. So being an Eulerian statistic means that the statistic has specific distribution, which is the following. Where this En is what is called the Eulerian polynomial. Eulerian polynomials can be defined mostly in 2 ways, either with a recursion, either with this generating series. So what we have is this LEC is this Eulerian statistic with this distribution. And so let me go back to our previous example with, okay, this is the first admissible pair. And I was kind of trying to compute the degree, but then I stopped because we didn't know how to grade this sigma. So in this case, we can see that the hook decomposition of 1, 3, 2 is given by this hook and this prefix at the beginning. So we only have 1 inversion here. So LEC sigma is 1. And the degree of this pair P is given by the degree of F, which is 1 plus 2 plus 2. So 5 plus LEC computed in this permutation here, that would give just 1. So we have that this admissible pair, this example has degree 6. Now, let me go back here. This was still our first slide. And now we know what these 2 objects are. what is not clear, of course, is that we have a bijection between this set of admissible pairs over n leaves and this set of admissible forests over n+1 leaves. And now I will give you a quick idea of how an algorithm that we found between these two objects may help to see the bijection between these two sets. Of course, we want the bijection to be graded, otherwise why would I define a grade on it, on this element, on these objects. So let's start from an admissible pair, so F sigma, and we want to define F prime, another forest. So here, sorry, this is very bad. Here we're assuming this pair to be in the set of admissible pairs over n leaves, and here we're assuming this forest to be on over n+1 leaves. So we start with these. So this is a forest F with 1, 2, 3, 5 connected components, and we assume our graded pair is given by F sigma, where sigma, let me just write sigma like this, is 1, 3, 2, 5, 4. Okay. Now, in order to define, or maybe let me give me a bit more space here. So in order to define an algorithm, we start ordering the connected components of F. So one can choose any method to define an order over this element. A nice one may be just looking at the smallest leaf we can find in its connected components. So here we have 1, here we are at 4, 6, 13, and 14. So one could say that this is the tree number 1, this is tree number 2, this is tree number 3, 4, and 5. Okay. The second step is looking for the decomposition for the hook decomposition of sigma. Hook factorization, actually, we call it. So here, this is a very easy hook decomposition. We have that 5, 4 is the first hook, is the second actually. 3, 2 is the first hook, and then we have this prefix at the beginning. Okay, so we want to end up with a forest which has 1 leaf more than F. So we start, of course, adding a new leaf. And this leaf, of course, will be labeled n+1 if n is the number of connected leaves of our tree. So we just add here 15. Okay, one could already stop. This is already a new forest, but of course we want the degree to be respected. And so the idea now is to add an internal vertex to this forest for every hook we found in this hook decomposition. So add vertex. Yes. Because when you have a forest, you know that the set of labels for the leaves is the interval 1n. So now I started with a forest with n leaves, so I already know that the labels used for these for the leaves are all the number from 1 to n. So yeah, if I only had a tree, I wouldn't know. But now I have a forest. So yes, I know that we are missing 15. Yes, please. Thank you. Okay, now I fixed it. So this is still admissible because I didn't change. Thank you very much. You know, I tried to do this example a lot of times, saying, oh, this is perfect, this is fitting. I had so many examples, but always you end up forgetting something. Thank you. Now, this is an admissible forest. I didn't have an admissible forest before. So as I was saying, now the next step is to add a new vertex for each hook I found in the hook decomposition of sigma. So a new vertex for each hook. I'm telling you this will be an internal vertex. And the way I'm drawing this internal vertex. So let's start. Again, I start scanning from the right. So I take this hook. This will be a new element. And now I'm adding an internal edge between H2 and the leaf I just added, and then between H2 and the two trees corresponding to the number appearing in this hook. So here I have 5, 4, so I'm drawing this. Now I go on and scan and find this second hook, and I draw a new internal vertex, H1. And now I'm connecting H1 to the previous vertex I added, the last vertex I added. And then the two connected components, in this case, there are two connected components associated to 3 and 2, which are connected components number 3 and number 2. And then I stop because what I had left was a prefix, and we don't really want to look the prefix doesn't really matter. So at this point, we had to add a degree to these internal vertices we added. And the degree I'm choosing for these two new vertices will be Q to the inv H2 and Q to the inv H1. Now, this idea of grading respects the first constraint I had in the grading when defining admissible trees. So you will actually find that the number of outgoing edges, so this degree is still between 1 and 2 minus the number of outgoing edges from the edges outgoing from these new internal vertices. So what we have is that the degree of this new forest F prime is equal to the degree of F plus the degree associated to these two internal vertices, which is just lack of sigma, because this is how I choose to grade these internal vertices. Okay, now we have an algorithm that starting from an admissible pair over n leaves gives you an admissible forest on n+1 leaves. One can go back. There is also a reverse algorithm that one can define, and I will just give the idea of this. So assuming we are starting from a certain f prime, which is an admissible forest on n+1 leaves, how do we find, in a unique way, of course, a pair f sigma, which is admissible over n leaves? So somehow we started knowing that this is the leaf we added. So what we want to do is to find this new forest by deleting everything that is over this highest leaf. So we are going to delete all these edges, all these vertices, and of course we are also going to delete all the vertices that were going out from these vertices I just deleted. So, okay, it is somehow easy to find a new forest which is over n leaves. Plus edges and internal vertices. Now, it is a bit less obvious that we are able to recover a unique sigma. And the way this is actually true is because the following fact that holds for Hooke. So it is given a list of numbers and inv H, one can define a unique Hooke. So if I gave you list 1, 3, 2. Wait. Sorry, I didn't prepare this example, and I don't want to mess everything up. So, but the point is that one can recover, given a list of number, one can recover a unique Hooke. So in this case, one will end up knowing that this Hooke over this internal vertex over here was above this 3 connected component. We deleted the first one, we had the other 2. And this 2 connected component has to be labeled with 4 and 5 because we can recover the order between the connected components obtained deleting this green part, this green tree. And so this is how one can go back and recover the pair F sigma given a certain forest F prime. Okay, so what we did so far is studying the bijection between these 2 family of combinatorial objects. Now, as I promised, now I will give you a geometric interpretation for these 2 sets of objects, and then also an interpretation of this bijection we just found. So I will start talking about okay. I will start talking about hyperplane arrangement and wonderful models. So in this first part of the second part, all I will talk about is more or less the result from a paper from De Concini and Procesi. From 1995. And when this is anyway. So Simona talked about hyperplane arrangement, saying this is a bunch of hyperplane, which is a very, very nice definition of it, very, very good definition. So we start taking V a certain complex space of dimension n, and we take A to be an arrangement of a bunch of hyperplanes, a finite bunch of hyperplanes. Okay, so in order to define a variety, which is called the wonderful model of De Concini and Procesi, one need to focus first on the poset of intersection of A. And then one have to make a choice, and this is the choice of a certain subset of P of A. Now, of course, later I will say that there are some nice property we want to hold for G, but for now, let's just say that G is a subset of this P of A. Now, for every element of G, so given G, one can define the complement of G, which we define as AG. This is just the complement of all these hyperplanes. Not even hyperplanes, they are subspaces at this point. And then one can define for every element of G, P of A, which is just the projectivization of this. Now, with this in mind, one can define the following maps from. The first one is just an inclusion of this complement inside this vector space, which is just Cn in our case. And the second one is a projection of the complement over this bunch of projective spaces we defined. Now, one can define, of course, this map rho, which is just behaves as I on the first component of this Cartesian product, and it behaves like PA prime over the components of this product here. The closure of the image of this map is what is called the wonderful model associated to G. This is a variety. And yes, just a small comment of the on the notation. Of course, this variety depends on G, because that's the choice we made. Now, with the H we are writing here is just to remember that we are in the hyperplane case, because later in this talk I will talk about wonderful models that can be defined up to a toric arrangement, and then you will find a T in place of the H. So this is what we have. So what we're actually work with is the projective wonderful model associated to this arrangement, which is as a very similar construction, but we take V to be a projective space. But all I will say holds the same way. So what we have when we end up with this variety is that some properties that holds for G, in particular properties that depend on the fact that G is a subset of this positive intersection, correspond to some geometrical properties that one want to study for this wonderful model. So, for example, if G has the property of being building, which we don't know what this means. Maybe someone already know what this means, but I didn't say it. And if G is building, it makes sense to define some subset of G which are nested. Then one can recover that, well, first one can recover smoothness of this variety. Then one can recover a description of the cohomology ring. A description of a basis of the cohomology. And then finally, also one can study the boundary components of this variety, even though we are not going to study this today. But and else. But today we are just focusing on the cohomology and the basis of the cohomology, starting from a given building set and its nested sets. So that would be the time of giving the definition of building a nested set. But instead, I would first talk a little bit about the case we studied. So the variety we reached and the hyperplane we were interested in. So we started taking, okay, in CTDN, we started taking the hyperplanes of type, the family of hyperplanes of type AN-1, like in Weil group AN-1, or like in the braid arrangement of type A-1. This is just a set of arrangement of hyperplanes Hij, where Ij is a subset of N. And Hij is the hyperplane is the following hyperplane. Now, the next step in order to have a building set and then to build a model is to study the poset of intersection of these hyperplanes. Now let's just have an easy example. What happens taking the intersection between hi and hj and at hi and hk in the case of j and k distinct natural numbers, distinct integers smaller than n. Then what we have is that it would be the set of elements in C to the n such that xi is equal to xj, which is also equal to xk. Okay, something I could mention too. And I want to call this element ijk. Okay, now let's take another easy example of the intersection between two hyperplane of this kind. So in this example, we want aj, lk to be 4 distinct natural numbers. And what we have in this case is that the intersection is simply xi equal to xj, and then xl equal to xk. And we want to denote this element of the poset as hij and then lk. So what we want to see here is that we have 2 blocks of variables that coincide. In general, it is not easy to recover the fact that every element h in this poset of intersection can be written somehow like h1, i1, i2, il, where these are subset of n with empty intersection. And the constraints that hold for the elements of this h, i1, i2, il is that all the variable indexed over elements which are in i1 are the same. And the same holds for every block appearing here. Now, this is the moment. Now we have a nice understanding of the elements that appear in this poset of intersection. We want to recover G. We want to make a choice. And the choice we make is that H is in G if and only if H is equal to what we would call HI. So one block appearing here. This is just a subset of elements. Okay. Of course, we have that I is as a subset of n of cardinality at least 2. Fine. Now, this is what we call G, and this, I'm telling you, has the property of B building. Now, word building suggests that one should be able to recover maybe the whole PA. One should be able to build the whole poset PA starting from this G. And this is somehow what happens. So the definition of G, of building set we have is the following for a given hyperplane arrangement. And this is a subset G in PA, such that if we take somehow, one can define, given an element L, some element of G that intersects transversally and generating building L. So yes, one somehow can call these can find these G factors for every L appearing here. Now, the G factor of a generic element of PA of this shape would be HI1, HI2 up to HIL. So this is a subset that has this nice property of being building, and that was the definition of building set. Now, as I anticipated, what we are also interested when studying this poset of intersection is some subsets of G with the property of being nested. And in this case, N is nested if given HI, HJ in N, either I and J are one contained into the other, either either they have empty intersection. Okay. So in general, given a building set, the definition of nested set is the following in general. So a subset of S such that given every subset of non-comparable element in it, then these are G factors, where G factors are defined over here, of a certain element of the positive intersection, which is not contained in G. Now, in our example, we have a nice interpretation, a nice picture one can draw for a nested set. So we are associating every element of G to a certain subset of elements from 1 to n. So if we take a bunch of points, then a nested set can be represented as some subset of the following kind. A diagram of the following kind. So here is a nested set, meaning that every circle we can find in this diagram can be associated to a certain I. Then we can associate to a certain element of n. One can see that in this picture, every subset of n, every two subsets of n are either contained one into the other, or they have empty intersection. And so this is what, and so this drawing of this diagram actually represents a nested set. And I think you can actually see why these are called nested set. Somehow it gives the idea. Now, as I had anticipated, we want to use this definition of building set of nested set to give a description of the cohomology of this variety. So we have this result from the continuum processi that describes the cohomology ring of the wonderful model of the wonderful variety as this ring. So notice that here we are taking the polynomial ring whose variable are in bijection with the elements in the building set. And now this is quite sloppy, sorry, but all I wanted to know to make you know is the ideal IG is generated by some polynomials which can be defined just in terms of the structure of the lattice of the positive intersection PA and some properties, some numbers that can be read in it. So for example, dimensions can be read in the positive intersection just by looking at the ranking of elements. And then we have some containing properties that can be still read. So this is this theorem from the continuum processi gives you the ring cohomology ring of this variety just by looking at something that you can read from the poset. And from of course, it depends on the choice of G. Now, there is this result from Gaifin and Zvisky. These are actually two papers that came out at the same time with a description of a basis for the cohomology of this variety, which is in terms of nested set. So the sets we just defined. And these monomial bases, actually these monomials that appear in the basis are called admissible monomials, rings a bell. And so it says that a monomial is an element of this basis that can be described if its support is given by a nested set, and then the variables have a certain exponents that have to satisfy some constraints that again only depends on the dimension of these elements, so it can be read from the positive intersection just by looking at the rank of the elements. Okay, so what we are saying is that if I have a certain nested set that now we know can be pictured somehow like this. Okay, then one can take this nested set, associate some exponent to every circle, every element appearing in this nested set, and then find an element of the basis. Now, another way of seeing this is is looking at these as a bunch of trees this way. So we take leaves for every dot appearing in this diagram, And then we take an internal vertex over these leaves for every circle appearing in this diagram. Now, of course, we have to encode also the information of this exponent. And we can do this by adding some labels to these internal vertices. So what we end up with is, again, a family of forests. And this is exactly the family of admissible forest we described in the first part of the talk. So somehow what we have here is this bijection. We are starting to see a pattern. Now, I don't have much time, actually, right? Around 10 minutes, maybe. So I will talk about this toric model, but of course, at this point, we expect to end up saying that the basis of this one of this variety is in bijection with this admissible pair, set of admissible pairs. Now, so we want to talk about toric arrangement. So this is everything I want to talk is from a paper by De Concini and Gaetti. Actually, two papers they're from 2018 and 2019. And so instead of starting from a certain complex vector space, one will start with a torus of dimension n. And inside this torus, one look for some layers. I'm a bit in a hurry, so I will just say that in our example, we are taking a toric arrangement of type AN again. And the toric arrangement of type AN has some subtori which are described this way. Or also one can see this. Okay, so this is a family of subtori one can define in this torus of dimension n. So what happens in the toric case in general is that while we had a nice positive intersection associated to a certain arrangement, we had that something a bit wilder can appear in this new positive intersection because one can have two different subtori that intersect in something which is not connected. This is not something that happens in general in a hyperplane array case. So what we have here is that things may be a bit wilder, but this does not happen in our example, taking this family of subtori as arrangement. In this case, what we have is that the positive intersection associated to these elements is actually isomorphic to the one we obtained while studying the hyperplane arrangement. In general, to build a wonderful model associated to a toric arrangement, one would need, again, a building set, which is an element in here, a set of elements inside this lattice of intersection. And there is something new. And this thing new is a fan, which has nice property respect to this element of these layers appearing in G. Now, this nice property are in terms of the way these layers are defined and the rays that appear in a certain fan associated in this certain fan. So it is in general not very easy to find an equal sign property fan associated to a certain building set. But in our case, we had that taking this fan as just the fan induced by the chambers of type of the Viola group of type AN. So these are exactly the same chambers that Simona drew over there in the last talk. one would end up with a nice fun and building set that allow us to build a projective wonderful model. Now, the construction of the projective wonderful model starts with an embedding of the torus T inside the variety associated to the fun, and then go on by blowing up the elements, blowing up the layers that appear in the arrangement after doing this embed, so inside this variety. So what we end up is what is called the compact wonderful model, the compact Toric model associated to the arrangement. In general, what we have is that this variety we ended up with depends on the choice of the building set and on the choice of the fun. But in our case, the choice of the fun was somehow natural, because we had this fun of type IN we could choose. So the model in our case would just be a Toric model of type AN-1. Now, what we want to reach is a description of the cohomology ring and a basis for this variety. So a description of the cohomology was given by the Concini in 2019. And again, what we have is a certain polynomial ring and a bunch of relations, and one can write some like a bunch of ideals. So now, of course, we expect that because everything depended on the choice of a building set and of a fun, we of course expect this ring to be in terms of the fun and the building set. So we have a bunch of variables that corresponds to the ray that we can find in the fun delta, and a bunch of variables that corresponds to the elements of G. Now, again, what we have is that these ideals here can be written and are generated by monomials and polynomials. Then one can describe just by knowing the positive intersection and the fun delta. And what we did together with Oscar and Giovanni was extending the result we had for the description of the monomial basis for the cohomology of the hyperplane in the hyperplane case, and translate it extend it to this Toric case. So what we have here is a description of some monomial that are actually a basis for this cohomology ring. Now, what we have is that these monomials are the product of two different monomials. The first one is uniquely in terms of the ray variables we had in this ring, and the second part is in terms of the variables associated to the building set. Now, the second part we already know corresponds to the nested set associated with some exponents that and can be defined just as and can be defined exactly as in the previous case. While the second part is actually some monomial. There are a cohomology basis of x delta prime. Now, we already know that these elements here are in bijection with admissible forests. These elements over here, well, for now, we don't know much, but I'm telling you that this x delta prime, this x delta Toric variety, when associated to a fun of type AN, are such that their Poincare polynomial is exactly the Eulerian polynomials of dimension n. So what we have is that this family of monomials we are using, this second part of family of monomials, is something that is graded like an Eulerian polynomial. So it's something that can be put in graded bijection with the set of Sn with an Eulerian statistic. In particular, one can choose Lek. the lag statistic. So what we have is that this monomial basis is actually in bijection with the family of admissible pairs over M. I did not tell you that this X delta prime fan actually depends on the nested set, and is exactly the X delta fan associated to AN, where M is the number of connected components one can find in this in the forest associated to this nested set. So I think I'm out of time. So that's just the very last thing. I wanted to go back to this slide and to say that so at the end, what we did was finding these three sides of the triangle. Now, this row over here comes from the fact that these two varieties are known to be isomorphic. So somehow how this work started was noticing that we had these two varieties isomorphic, knowing that we had these two bijection. We were curious and we wanted to find an explicit bijection between these two sets that would give an explicit bijection with element of the basis of the first and the second variety. So I'm going to stop here. Thank you for your patience. Thank you.
Any quick questions?
How many elements there are in AF n+1?
Yeah, this is a nice question. Actually, I had an extra slide. So what we have is that, so the answer is that I don't know, but there is this this series, generating series that one can compute, and which counts the number of trees with k leaves and degree I. This exponential series has this generating function that one can solve and obtain the number of connected components, and then with this exponential of this series gives the number of forests one would expect, and is great with a certain degree and with a certain number of leaves. So one would end up knowing exactly the value of the Betti numbers given n. Yes.
Other questions? If not, let's thank Viola again.
Yes.
So to study a group G, so you study groups acting on spaces. So you have some space X, and then you want to study G. A good way to study G is to look at the action of G on some interesting spaces X, and that's basically what is the goal of what is the GGT about? Geometric group theories is studying groups via actions on spaces. Now, a particular nice space to study. It's very heavy, this board. So a particular nice space to study is E under bar G. So this is a space called the classifying space for proper actions. Let's say classifying a G space because it's as a G action. And in a second, I mean, I will give you a formal definition now of this, or semi-formal definition of this, but then I will argue why it is an interesting space, because a lot of examples are actually these E under bar Gs. So what is this E under bar G? It's a G space. So E under bar G is a G space. And the following properties uniquely determine it, and it always exists. Well, I will not prove for you that it exists, but I can tell you what the properties are. So the first one is it's a G-CW complex. So it's an equivariant CW complex. I do not want to define this. We had CW complexes today, and I believe also yesterday. Well, CW complex is something built out of disks and spheres, right? And the GCW complex is something built out of equivariant disks and spheres, like things like this. You know, you take a disk and then you cross it with a coset, and then you glue these things with each other instead of just gluing spheres and disks. So that's what an equivariant CW complex is for me. Okay, so and let's say built out of such cells. That's the first property I need. And the second one I need is I have to have some explicit prescribed fixed point data. So here, this is the fixed set with respect to subgroup H, where H is any subgroup, let's say, in G. And this has to be of a specific form if you want to be in underbar G. So it has to be empty if H is infinite. And it has to be contractible, so homotopy equivalent to a point, if H is finite. So hence the name for these proper actions, because, well, proper actions have finite stabilizers, and so as you see, this space has only finite stabilizers. So in fact, for any G space with a proper action, there is up to homotopy a unique map into this thing. So it's actually a terminal proper GCW complex. Okay, so this thing is unique up to G equivariant homotopy equivalence. Okay, so that's a formal definition. It exists. It's unique up to G equivalent homotopy equivalence. So why does it show up in geometric group theory? You can ask this question. And I mean, I'll give you immediately examples. Well, the best example you can take is like probably your favorite group is infinite. I mean, well, let's try with the finite groups first. That's even easier. So say G is finite. Well, then the story is boring. You can take E under bar G just to be a point. So finite groups is not really interesting. It really is interesting here is the case of infinite groups. Maybe I think my title officially was not just Euler characteristic of groups, but of infinite groups, because, well, that's what I'm really interested in this talk. Okay, so finite case is pretty boring. Well, the next, your favorite example probably of non-finite group is obviously the group of integers, and in this case, E under bar G is well, as I said, it's unique up to homotopy. So I need to find one model for such a thing, and then I can call it E under bar G. So a model for E under bar G in this case is R with the usual translation action. Well, that's a very nice model for that. Well, so in particular, like you easily see that fixed point data with respect to this Z on R, the only non-trivial fixed points you can have is for the trivial subgroup, because, well, all the other finite subgroups of Z, every finite subgroup of Z is trivial. So there's not much you have to really check here. So it's actually a free action. Okay, so that's the second example. Let's make it a bit more complicated, bring in some torsion to have a bit more fun. So we can look at infinite dihedral group, which is a free product of Z mod 2 with the Z mod 2, which is the same as a semi-direct product of integers with Z mod 2. You can choose one of the conjugacy classes, and then and that gives you such a decomposition. And in this case, again, a model of E under bar G is a real line. This time, the action is translation and reflection. And this is now a non-trivial model of E under bar G with an interesting torsion also inside. And this is sort of like one of the basic examples also of geometric group theory, where you have this nice E under bar G model. So now I'll make things a bit more complicated and give you a couple of examples which I am personally interested in while working with this kind of groups. So the fourth one maybe is an example of, let's take G to be gamma G, So this is the mapping class group. Mapping class group of surface of the surface of genus G. So this mapping, I mean, I think I am in Pisa. Maybe I should not define what's mapping class group because I think people know it here. But well, because we have also guests from other places, maybe I'll just recall. I mean, surface genus G, of course. I was in a conference once, and someone joked that every talk in topology should contain a picture of a manifold, and that's my picture. So so you have this G many holes here, so like G many. So genus is G, and so mapping class group is just like you can take. Well, I mean, you can take self-diffeomorphisms of this group, of this surface SG. You can take self-diffeomorphisms and divide by the component of the identity. It's like that. Yeah, so that's the gamma G, or like it's also the pi zero of this, if you want. Okay, so this is a mapping class group, but now why is this interesting? Well, this is interesting because there is a very nice example also for Yanda-Bar G in this case, and that's this famous Teichmuller space, which is the modular, which is basically the space for all possible complex structures on this this surface. So that's the Teichmuller space in G. Well, in fact, it's like a homeomorphic to large enough 6G plus 6 or something like that of dimension Euclidean space, but it's a very interesting space. And then, in fact, if you take the quotient of these by the gamma G, then that's the moduli space of the surface of genus G. Okay, so as you see, Yanda-Bar G shows up in this type of geometric situations as well. The fifth one, which is also a very interesting example, you can take G is equal to SLN Z. And this example sort of generalizes to any lattice in a Lie group, also in like the arithmetic situations, like arithmetic groups, etc. But this is the most basic example. So in this case, you can take Yanda-Bar G, a model for that to be the symmetric space, which is SLNR divided by SON. Well, this still has an action of SLNZ, and so this gives you a nice model of Yanda-Bar G. Well, I'll tell you also sixth example. I'm not sure how many of you have seen this much, let's say, technicalities, but a very famous example also of such a Yanda-Bar G. Well, for people who are certainly interested in moduli of abelian varieties have seen this example. So if you take something like that, then Yanda-Bar G is the so-called Ziegel's upper half plane. Okay, so that's the variety of examples. I could go on now and tell you more, but this now convinces you that Yanda-Bar G is an interesting space to study. Okay, so now a condition I want to ask, a new condition I want to ask is, well, assumption, which is the standard assumption in geometric group theory, which you often work with. And this is what I will be doing as well here, even though I'm not a geometric group theorist. But, well, if they work with this assumption, who am I to try to make it more general? So the assumption is that the G admits a finite model for Yanda-Bar G. So what does this mean? That means that I told you this is a GCW complex. So in other words, there exists a finite GCW complex model for E under bar. An equivalent way of saying this is that if you just take the quotient, this is a finite CW complex without any G, finite CW. Sometimes the terminology here is co-compact, because when you quotient it out, it stays compact. Okay, so that's a finite E under bar G for you. Now, well, you may immediately complain looking at these examples, but well, in some of your examples, they are not finite. For example, well, certainly second and third are finite because you quotient that thing out is like a circle or an interval. That's the first and second. The fourth one, moduli space is not compact in general. Like if you take the quotient of the diagonal space with the mapping class group, it's not compact. But there is something called the curve complex, which is like some kind of a deformation retract of this diagonal space. And if you quotient that out by mapping class group, that is compact. So it has a co-compact spine inside it. If you have seen, it's similar to this spine of geodesics inside the hyperbolic two-plane. Okay, so the same applies to this and this. Obviously, these are also not co-compact, but there are these spines inside here, inside here. In particular, when n is equal to 2, that's this famous tessellation of the hyperbolic plane, and then you can see that there are equivalent spaces to these, which have this property that they have a finite model of E under bar G. Okay, so that's sort of the assumption I want to work with. Now, what does this buy me? Like, what is the... yeah, okay, so in this case, also another model for co-compact E under bar G is the so-called Borel-Sayers compactification, which I don't know if you have seen or not, but like people, other type of arithmetic examples, like arithmetic groups, like you can always construct this co-compact E under bar Gs. Okay, so now, what does this buy you? I mean, why is this assumption nice? So one of the immediate applications I can give you is, well, the general review. Let's do the group cohomology. I'm assuming people have seen at least singular cohomology in this audience, so I will assume it. So if you take cohomology of a classifying space of a group G, so you take a cohomology of BG, where BG is the usual classifying space. Well, there are many ways to define this thing, and one of them is the classifying object for principal G bundles, if you want. So it's the classical topology. So if you take cohomology of BG with rational coefficients, well, this is very much boring when G is finite. For G finite, this is kind of a boring stuff. It's just Q in degree 0 and 0 else. That's a well-known fact. Okay, so that's good. But of course, well, for infinite groups, this is an interesting thing. So cohomology of BG, Q in general, quite interesting and difficult. Interesting and difficult. And for example, in the case of the above examples, starting from mapping class group, SLN and SPN, they are actually not even computed. Computation of these rational cohomologies of arithmetic groups is a big industry, and one of the things that like is also related to all this Langlands program and things like that. Okay, so this is interesting. So, well, it turns out that if there exists finite E under bar G, so if the assumption is satisfied, then the cohomology of this, and the total dimension of this rational cohomology as a graded object is finite. Well, this follows actually from a very simple observation that if you take cohomology of BG, in fact, because of this here, that for finite groups, the cohomology looks so simple, turns out that this is the same as rational cohomology of this E under bar G divided by G Q. And now I told you this is a finite CW complex. And that gives you a bound on the dimension of cohomology. Okay, so a priori, it is absolutely not clear why this should be finite dimensional, because, well, in general, it is not. But if you ask for this, then it is, because there is this isomorphism. And you also see that if it's not finite, then you cannot expect that this will be also finite. I mean, why should it be? It's a rational cohomology, and there are groups which have infinite dimensional rational cohomology too. But the reason for this isomorphism is exactly this observation here. Okay, but now this allows you to talk about Euler characteristic of this group. So you can say, what's the Euler characteristic of BG? Well, let's denote it like this, chi Q, because that's the Euler characteristic with respect to rationals. And let's do it for G. I don't want to write BG. I just call it Euler characteristic of G. And well, Euler characteristic of G, of course, by definition, is the alternating sum of dimensions of these cohomologies. Well, you may ask me why I'm doing cohomology and not homology, because, well, later I want to work cohomologically in this talk, but you could also do homology if you wanted to. So you have this alternating sum, and what is this sum? Well, turns out that there is a very, this is in general tricky, because then you need to understand exactly these cohomology groups, but, well, there is a better way of doing it. And this isomorphism now tells me, well, problem is that this is a priori an infinite space. As far as G will have a torsion, BG is an infinite space. So you can't use the cell structure of BG to compute this Euler characteristic. But this thing here is finite, so I can use cell structure of that to compute the Euler characteristic. So this is -1 to the n alpha, where in alpha, so where the sum runs over all G cells. So alpha is a G cell. Well, alpha is a G cell of E under bar G. I don't know if this, can you read this? G cell of, how does this go up? G cell of E under bar G. I think I'll lift this up. So it's the G cells of E under bar G. So E under bar G consists of equivariant cells. There are exactly as many equivariant cells as there are non-equivariant cells for this, because I'm dividing the G out. So either you can number it on the non-equivariant cells of this or the equivariant cells of this. And alpha is just the dimension of this cell. Dimension of this cell, alpha. Well, you can think of this alpha as some kind of typically like some G mod H alpha times dn alpha or something. And you take all possible these cells on this finite model of E under bar G, and then you sum the -1 to the n alphas, okay? So that gives you a formula for Euler characteristic, which is quite useful. Okay, but it turns out that this invariant, to compute this rational Euler characteristic of groups, is notoriously difficult. Like, not just the cohomology of these things is difficult. As I told you, for such arithmetic groups, it's so difficult to compute. It turns out that even the rational, even the Euler characteristic of these things is difficult to compute. So people introduced a new invariant, which is well, I think it's originally due to Quillen and Sayre, but then later Ken Brown generalized it a lot of this. So there is a different invariant that is used to compute this invariant, which is one of the basic invariants for groups. I mean, you want to study as far as you are interested in group cohomology, but like if you can't compute it, well, maybe at least you can compute this, but this is also difficult. Different invariant, and this is called the orbifold or orbispace Euler characteristic. In fact, geometric group theorists call this the actual Euler characteristic, which is for me a bit strange, because for me the characteristic is something like this rather than what I'm going to define now. So this orbifold Euler characteristic is defined as follows. So here I took the sum of these signs over the cells of E under bar G. So I'm going to do the something same. So I'm going to now define for you this orbifold Euler characteristic of G as a sum. Again, alpha runs over cells of G cells of E under bar G. So I take all possible equivariant cells like that. And for each of them, if I put here -1 to the n alpha, that is the old Euler characteristic. But I'm going to do something funny. I'm going to divide this by the cardinality of every H alpha, which is the stabilizer of this cell. So I am sort of normalizing these terms by the stabilizers of the cells. So there are other ways of defining this thing, but this is one of the ways of defining this thing. It's independent of the choice of the model of this E under bar G, and it's well defined. Again, the assumption is always there. Otherwise, this does not make sense, because I mean it has to be a finite sum. Okay, so that's the orbifold Euler characteristic. And now, how is this used to compute the usual Euler characteristic? Well, Brown proved the following result. Brown proved the following theorem that well, under these assumptions, the Euler characteristic with respect to rational cohomology of G can be written as the sum of these orbifold Euler characteristics of CG, where G runs over something which I will write down. So G runs over conjugacy classes of finite order elements. Runs over conjugacy classes of finite order elements, and CG is the centralizer of G. So if you understand this type of invariance and you understand the centralizers, then you understood the Euler characteristic of G. Now, I will give you some examples how far these things are computed in interesting cases of like more arithmetic sort of cases. Yeah, so I think I need to maybe look up my notes because there are some numbers I don't remember. So, right, so let's look at the orbifold Euler characteristic, for example, of the mapping class group. And this is a famous result. This is equal to the special value of Riemann zeta function at 1 minus 2g divided by 2 minus 2g. And this is a result by Harrer and Zagir. So this is an interesting number, turns out. These numbers are quite well studied. I mean, they are, of course, describable in terms of Bernoulli numbers. But, well, still there are some few things conjectured about properties and behavior of these numbers. So that's a good example. But, for example, then using this kind of stuff, you can also give a formula for this, but I can't write down it for you. Because Harrer and Zagir do this in their paper, but it's extremely complicated to actually write this down. I mean, it's some big sum with some weights and things like that. And this is usually much easier thing to compute. This is actually also in this case computed, but it's tricky to write down. You can immediately see that the centralizers in this case are lower dimensional mapping class groups. And then you can imagine you will get a bunch of sums of these things indexed on how many conjugacy classes of such elements you have here, which is often also understood. That's very unfortunate notation here. This G and this G are very different. Maybe I'll write here gamma so that you don't get confused. Gamma here and gamma here. And then G is, of course, the genus. Otherwise, otherwise there's too many G's at the same time with different content. Okay, yeah, so then another interesting example I can give you is the orbifold Euler characteristic. I put now orb in bottom, but orbifold Euler characteristic of symplectic group of 2GZ. Well, these and these are, of course, related geometrically because there is a very natural homomorphism going from here to there, with the Torelli group being the kernel. So there is some relation between this formula and what I'm going to write down. So this is the product of special values of theta function. And this is a result by Harder. Günther Harder proved this in 70s. Okay, but the rational Euler characteristic of these things is not computed. So in general, it's an open problem, a very complicated open problem directly related to arithmetic geometry. Like it's not really known how far this can be computed. The highest one I found after consulting with some experts was that SP18, for example, is computed, and that is 528. That's how far I know. The biggest, highest advance in this direction, computing Euler characteristic of the symplectic groups, which is crucial for understanding moduli of abelian varieties, which is one of the most important things people study in arithmetic geometry. This uses Langland's program, basically. Like, I think it does use the Arthur's trace formula, which is one of the things they use in arithmetic geometry. Okay, so as you see, I told you now the classical story. When did I start? 10 past or something, or 7 past something? Okay, so that's the story for this kind of invariance. Now, one thing you observe here is that all these examples just use rational cohomology. So I'm never really talking about any kind of cohomology that contains torsion. And there is a reason for that. I mean, you probably obviously know, and there is a reason for that. I'm just deleting this reason. Well, I'm talking about rational cohomology of, before I delete this, let's keep this. So the reason for that is this result, that for finite groups, rational cohomology is so simple. For finite groups, rational cohomology is so simple, and because of this, in the case when you have finite E under bar G, you can eventually still have finite dimensional rational cohomology. But obviously, nothing like this can be done. Like if you look at cohomology of PCP with FP coefficients, of course, the dimension of this thing is infinite. This is infinite dimensional. And so what is the FP Euler characteristic of PCP? Well, I have no idea what that is supposed to mean, because, well, I can't write down the alternating sum of cohomology groups. Well, this we know very well. This is the cohomology of the length spaces. It's the FP in every degree. Okay. Well, but it turns out that there is a, well, but this is cohomology. This is the classical singular cohomology, which we study in the school, and we've known this from the very beginnings of our mathematical education. But well, there are more fancy cohomology theories. There are more fancy cohomology theories which allow you to actually compute more stuff, and this is the generalized cohomologies. Well, the generalized cohomologies are your usual good old cohomologies, satisfying all the properties you know. When you study cohomology, you learn about this Mayer-Vietoris, homotopy invariance, excision, blah blah blah. All of these things are true for generalized cohomology. The only difference is that when you are computing cohomology of a point with FP coefficients, or say with the Z coefficients, well, the singular cohomology, of course, with any coefficients A, let's say, well, it's A when this is 0 and 0 else. Well, this is not true anymore for generalized cohomology. So that's the only difference between generalized cohomology and usual cohomology. Now, what I want to consider today is a generalized cohomology called Kn upper star. So this is the nth Morava K theory. And I will tell you what this is when n is equal to 1 and n is equal to 0. So this is the nth Morava K theory, and this is always over a prime P. So in fact, the notation should be Kn comma P upper star, because it always exists over some prime. But I want to skip that prime and just fix that prime, and I will be always working now over a prime. So I'm interested in this torsion stuff. So you can take this Kn star like that. So what's the property of this? Well, this is a generalized cohomology theory, and it has the property that if you take cohomology of a point, it has a very interesting description. It's not like this. It is very similar to what you have seen in complex K theory. Some of you have seen what's spot periodicity. And so the cohomology of a point looks like Laurent polynomial algebra over Fp. Well, the usual cohomology would just have Fp in degree 0, but this has the Fp in many degrees. So this is a variable Vn which has a degree 2Pn minus 1. So in particular, when n is equal to 1, you can think of K1. It's not exactly the same, but it's the usual complex K theory. It's basically equivalent to usual complex K theory. Complex K theory mod P. So complex K theory is the cohomology theory built out of vector bundles over a space. And then you consider that mod P in a certain way, in a derived way, not like just on the nose. And so when n is equal to 1, this K1 is like basically complex K theory, but mod P. And in general, this is some general version of that. Now, why is this interesting cohomology theory, and why should we care about this stuff in this context of groups? And I mean, this is what I've been trying to, let's say, advertise the last couple of years, that we can actually try that in this context to use such cohomology theories. And the first observation is due to Ravenel, was Ravenel proved that if you take Kn upper star of Pg, so you take this generalized cohomology of Pg, as opposed to this situation here, this is, so, well, let's say let G be finite, let G be finite. Then Kn upper star Bg is finite dimensional over Kn upper star of a point as a graded ring, which is Fp Vn plus minus 1. Okay, so what does this mean? Like, let's digest this a bit, because, well, I'm not really in a rush and I'm trying to explain these things a bit more carefully. So Kn upper star of NEX is a module over Kn upper star of a point. That just comes from the external product in cohomology. It's always a module over Kn upper star of a point. But now Kn upper star of a point is a graded ring. In fact, it's a graded field. I don't know how much homological algebra you have done over graded rings, but homological algebra over field we would know very well is just semi-simple. It's everything is zero dimensional, so there is no non-trivial X, Tor, etc. And you can talk about dimensions when things are finite dimensional. The same applies for graded fields. It's the same. So if you work over graded fields, everything is semi-simple. As far as you are finite dimensional over this thing, as a graded module, you can talk about dimensions of these objects. You can talk about the size of the basis. And so what you can do now is using this result by Ravenel, you can define what is Kn theoretic Euler characteristic of Pg. And that is the, well, here I need to be a bit careful. So when you do usual Euler characteristic, you sum the even ones, odd ones, and you subtract from the evens, odds. So you can do the same here. So you can take the dimension of the Kn even of Bg and dimension over this here. It means over this now, dimension. is dimension over k and upper star of a point. I need to take dimension over which I am finite dimensional. Otherwise, what am I talking about? If I just take dimension of this thing over fp, of course, that's infinite dimensional, but I'm taking dimension over that. Minus the dimension of the odd part. And then again, I'll take a bit my time to explain that, well, this variable Vn is in even degree. And so the action of this Vn, so the action of this graded ring on anything, only sees even parts and the odd parts. So even and odd part are sort of not talking to each other when it comes to the module structure, because the variable is in even degree. So therefore, I can take the even module, the odd module, and subtract them. Okay, so that's the very interesting invariance for finite groups, turns out, as opposed to if you would define just Euler characteristic for, in this case, for finite groups. Comment here is that you should think of when n is equal to 0, k0 is just a rational cohomology. So the k0 can be taught as the rational cohomology. That's one of the obvious observations as well about this stuff. Okay, so either way, so here is maybe I'll delete the board and write this down. So here is a theorem by Hopkins, Kuhn, and Ravenel. Which says that you can always compute this in terms of G. So theorem, that's Hopkins. I'll take a new chalk. So Hopkins, Kuhn, and Ravenel, what they prove. What they prove is the following, that that you can consider G and P, Gn comma P, which is the following set, G1 and so on, Gn, tuples of elements of G, with the following property that each of Gi has P power order. It's P power order, and they commute. Gi, Gj is the same as Gj, Gi for all I and j. So this is a very nice set. And then you can act on G, act on this thing from the G. So G is acting on this set by taking G times a tuple like this, is just a conjugate all the coordinates. So that's how you act on this thing. And well, what Hopkins, Kuhn, and Ravenel prove, HKR theorem, is that for G finite, this Euler characteristic says a lot about the P power torsion in this group, namely tells you that this is exactly the cardinality of G and P divided by this G using this conjugation action, and then the cardinality of this set. So that's a very nice description of this Euler characteristic. Now, before, when I was talking about infinite groups and in the rational cohomology, I told you that this result that I was understanding cohomology of finite groups was crucial. Well, and in that case, the description was super easy, and some things were actually easier in this case. But now I also I do not understand cohomology of this BG in total for finite groups, but I do understand at least the Euler characteristic, and I understand it quite well. So the question is, what can we do in order to maybe say more about infinite groups using this KNs? And so this is where we come in the game. So we started to realize that these things, what you did for infinite finite groups, also in this case can be generalized for infinite groups. And this has its own story, and I will tell you about this story in a second. So first observation is that if G is infinite, with finite E under bar G. So, well, not necessarily infinite, but if G is a group with finite E under bar G, then there is a spectral sequence. There is a spectral sequence which looks like this. Well, it doesn't really matter if you really want to understand what this E2 term is, but I just draw it to tell you something as a consequence. So if you have the finite E under bar G, and if you know Ravenel's result, then you can prove that this E2 term is always finite dimensional. So this is finite dimensional over Kn upper star of a point. So finite dimensional now, of course, means over that ring. As a consequence, you conclude that also when you assume that you have finite E under bar G, this is also finite dimensional using the spectral sequence over Kn upper star of a point. So in particular, exactly as in the finite group case, you can talk about the Euler characteristic of Bg as the dimension of the even part minus the dimension of the odd part. The other observation is that if G has, here the G was finite, but if G has finite E under bar G, so if G has finite E under bar G, so if G admits finite E under bar G, then this set again is finite. So why is that? Well, it's a well-known fact that if you have finite E under bar G, then you have finitely many conjugacy classes of finite subgroups in your group G. That's a restrictive finiteness condition. So in particular, this set of tuples, of course, is not finite, but the quotient is finite. Okay, so then we arrive to the generalization of this result by Hopkins, Kuhn, and Ravenel. So here is a theorem which I proved together with Wolfgang Schluck and Stefan Schwede. So this result says the following. Let G be a group. Let G be a group with finite E under bar G. Then it turns out that there is a very nice formula for computing also the Morava-K theoretical Euler characteristic of this group G, which gives the sum over the elements G1 and so on Gn belonging to this quotient. So I'm taking all the representatives of this this quotient. If I write here 1 now, well, that's this old formula. It's just the cardinality of this. But I'm not going to do that, of course. For finite groups, I should be writing here 1. But for infinite groups, you should be writing something funnier, which is the rational Euler characteristic of the classifying spaces of the, well, I told you that I will remove this G here everywhere. Now I'm writing here BG. I should be removing this G. I mean, I should, I don't know. I think I should just call this, I should remove this B everywhere. Like when I do the Euler characteristic, I should just do G. I don't want to drag around the B here as well, because I told you I will not use the B. Okay, so here is the rational, so Kn G, which by definition, of course, is the Kn of Pg. And here the centralizers of G1 and so on, Gn. So this here is the centralizer. This here is the intersection of centralizers of these individual elements. So this is the result what we proved. And here are several comments about this result. So one is if G is finite, of course, these centralizers are finite. And then the rational cohomology is very easy. And the rational Euler characteristics are just 1. So it does tell you that it specializes to that. But of course, we are using the Hopkins, Kuhn, and Ravenel to prove that. So we're not really obtaining anything new for the finite case. A funny thing, though, is that when n is equal to 1, this was a well-known result. This was a result due to Luc, Oliver, and Alejandro Adem. So when n is equal to 1, this formula was well known. And the funny thing is that for n is equal to 1, this formula was known. And then you also had all this Hopkins-Kuhn-Ravenel character theory. But and this was here obtained with the completely different methods when n is equal to 1, like purely K-theoretic methods. And nobody really tried to combine until now these two things. Like this was sort of the world of geometric group theorists when n is equal to 1, and they were doing some stuff with it. Whereas here, this was like chromatic homotopy theory. And now somehow this result combines the old results by these people and those people and obtains this this new result for higher ends. Now, what are the applications of this kind of formula? I mean, obviously, so far the only applications I have is to explicitly compute some stuff. And the hope is, well, I can tell you, for example, I don't have this formula anymore, but I wrote down this formula due to Brown before, which was about computing rational Euler characteristics in terms of the orbifold Euler characteristics of centralizers. These formulas were used by Brown to obtain some new results about special values of zeta functions. And he really used these formulas. So the hope is that because the rational story is some sort of a special case of this chromatic story, that in certain cases we can say more about the values of these zeta functions if we use formulas for Kn instead of just Q. So, and I can tell you what type of formulas and flavors of the formulas I'm talking about, even though until now I do not have a new application for like some data numbers using this stuff, but there are a lot of formulas which tell you that if you look at more interesting examples, potentially you could get there. A part of the fact that to compute such invariance for infinite groups is anyways interesting and useful, because it does show you how much these cohomology theories see about your groups. And it's sort of new invariance of these groups as well. So I'll give you a couple examples where I so far managed to compute these Euler characteristics. I mean, to compute more, I need to go deeper into number theory and geometric group theory, I believe. So the one is you can take K. So first example where I managed to compute stuff using this theorem is you can take K to be a totally real field. Totally real field. That is a field, it's a number field which all inclusions into complex plane are actually in the real plane. So totally real field, like for example, real quadratic field or something like that. And then using this theorem, you can compute what is the Kn Euler characteristic of SL2 of OK. And already here, interesting results come out. This gives you a formula which tells you that here's a formula. This is 2 times zeta k minus 1 plus the conjugacy classes h b to the n minus 2 divided by h. Okay, so what are these things? These things are zeta k is the Dedekind's zeta function. Dedekind's zeta function. Zeta function. I mean, it is Riemann zeta function when k is equal to q, but in general, it's not the Riemann zeta function. And here h runs over conjugacy classes. Conjugacy classes of maximal finite subgroups. Turns out that they are all abelian in this case. And if they're all abelian, you can talk about this p local part. And this is the nth power. And this n is exactly reflecting the n here. And this is some h. Now, it's a funny thing that this is telling you that, that even though here are some rational numbers, well, whatever this zeta contains here, these all things cancel out and you get something integer. So this is the type of application I'm talking about. Well, in fact, this formula itself doesn't give you anything new in these terms, because when n is equal to 0, well, this just generalizes when n is equal to 0, a formula by Brown, the one I was talking about. When n is equal to 0, Brown proved this formula and obtained new results about this zeta values. Like some denominators of this zeta function have this and this properties. This in general is not computed, the special value of the zeta function. I mean, it's a big tables for this, but not really computed. Well, not in this case, but in general, the goal is to do enough computations of this using this stuff so that eventually you can potentially say more about these things. Here we are just unlucky that you end up with this term instead of something more interesting. But in any case, this is a generalization of a classical formula to Brown and I will say here harder as well, because partially this was also due to harder. Okay, let's go for more examples of computations. Another example. Well, in the case of SLN, the things are boring, so I will not do that. So let me do the case of SPN. So let P be a prime, and let's work over the prime P. And then you can take the symplectic group P minus 1 Z. P is a prime, let's say odd prime. Prime bigger than 3, I think is better. So you can take this kind of symplectic group, and I told you that this had some very nice descriptions of orbifold Euler characteristic, also in terms of zeta functions. And then you can take the Kn Euler characteristic of that. And here already you see that something very funny comes out. So namely, you get the rational Euler characteristic of this thing, which is hard to compute. As I said, this is not in general computed. But then something funny shows up, plus Pn minus 1 divided by P minus 1, 2 to the P minus 1 divided by 2, and here HP minus 1. So what is this HP minus 1? HP minus 1 is a class number. It's a relative class number. It's the class number of the zeta cyclotomic integers divided by the class number of the real part of this cyclotomic integers. And so one of the simple observations you can make here is that when you go here on the limit when n goes to infinity, and that's a recent observation by me, that this is another place where these kind of formulas can be interesting. Well, first of all, this is impossible to compute, as I told you, but the difference between this and this is purely number theoretic, you see. And when n goes to infinity on the limit, these are all integers. Now, what do I mean when n goes to infinity, the limit of integers? Well, I'm working, of course, in the p-adic numbers. So the p-adic limit of these will give you p-adic limit of that plus this part here. And so if you see in the p-adic limit, there is only p minus 1 as a denominator, which does make sense because, well, this better be a p-adic number if I go to the limit. I can't have p inside here. This is a p-adic integer in the limit. So you can again use this type of games. The fact that you know that this side has no denominator in p, depending on what you would get here. For example, you have to argue why this is an integer. And obviously, there is some class field theory you can use, and then you can conclude there is an integer. This surjects on this, and then like just the index is divisible. But a priori, if you wouldn't know that this was a number that had no denominator p inside, these type of results can give you that. So that's one of the another potential applications of this formula, part of the fact that you are actually computing some stuff in terms of number theory. And the last example I will mention was the mapping class groups. Another example here, I computed the simplest possible one, and the next. So in fact, you can look at this also in the same case when prime is bigger than 3. You can look at the Moravec theoretical characteristic of the mapping class group p minus 1 divided by 2 genus. Turns out that this is Pn minus 1, p plus 1 divided by 6 plus the rational Euler characteristic again of this, which is computed. Now, 2 observations here, and then I finish my talk, is that one is that when you take something more complicated, you can take also here gamma p minus 1, then the formula becomes more complicated. and my PhD student James Fleming is working out that case. And another observation here is that if you look at these numbers this year as well as this year, by some congruences, mod ZP, they are both related using glass number formulas to the previous special values of zeta functions I was talking about. So these zeta numbers again actually show up here as well as here. So this is the p fractional part of that zeta 1 minus, I think zeta 1 minus 2p or whatever I wrote at the beginning. So as you see, these numbers already show up in this case. Okay, I think I'm done. Thank you very much.
Is there any question?
So do you have some results saying that the Euler characteristic for Kn is bigger than the one for Kn minus 1? Or do you expect something like that?
Okay. Yeah, I mean, I don't know in general because, well, yeah, this is a good question. I mean, yeah, I believe that in general this probably wrong because, well, I mean, I'm not even aware, like, is it obvious that for finite groups that is true? I mean, even though we have more tuples, well, I think maybe for finite groups that is true by just this cardinalities, and you see that you take more tuples, but here, because you have these centralizers, maybe some funny things are happening because these centralizers can have also negative Euler characteristics sometimes, you know. So maybe actually, okay, so, well, in fact, for infinite groups, well, for finite groups, I think what you are saying is right because, well, we just look at these cardinalities. But for infinite groups, you can actually have that when n increases, these things become more and more negative or something like that. I think I can maybe show you example afterwards. At least you can have cases when this becomes negative. And then I think in the limit maybe also negative. The problem is that these can have negative Euler characteristics. And when you increase the number of these g's, you can get more and more negative numbers, which of course does not happen for finite case. Yeah. So therefore I don't, but I think I should think about it more carefully.
Thanks.
Good question.
There is some property like if we have an exact sequence of groups and how this Euler characteristic behave.
Yeah, it's the difficult thing because, like, for rational cohomology, you have this Lindon-Hochschild-Serre spectral sequence, which will basically, well, it will basically tell you that there is a way of relating if you have a short exact sequence or the characteristic of these different things. In this case, you have this generalized Atiyah-Hirzebruch spectral sequence, which basically is that you will have something like, if you have an extension like this, then what you know is that you are getting, I think, cohomology of G mod H with coefficients in K theory of this BH converging to the K theory of BG. So in general, there is no K theory of that involved in the spectral sequence. And because of this, you can't expect a relation between K theoretical Euler characteristic of this, K theoretical Euler characteristic of this, and K theoretical Euler characteristic of this. So I'm not aware of any identity like that.
Okay, thank you.
Your question?
Yeah.
This is a very silly question, but because everything is now related to geometric group theory. Geometric group theory is related to core structures in the group. This is homology of infinite groups we are interested in.
Yeah.
What happens, do you know, if anything happens for locally finite homology theories?
I mean,
any
what is a locally finite homology theory for you?
coarse homology theory?
I haven't looked at it. It could be that some of these techniques can be generalized to more fancier cohomology theories, but I haven't tried. Yeah, so I don't know the answer.
Any other questions? If not, let's thank Irakli again. And thank you for coming.
Thank you.